Ready? Hello, everyone. My name is Don Webbles. I'm the chair of the Global Environmental Change Focus Group, which now has almost 13,000 members within AGU and growing. And so we expect before long we'll take over AGU. That is a joke. Last year we had the first special lecture in honor of Steve Schneider, a very close friend and great contributor to our understanding of climate change and to climate science in general. At that first lecture, the speaker was Michael Oppenheimer. It ends up that we've had over 10,000 hits off of that lecture to watch that lecture since. It's the most from any lecture given at AGU last year. So we're kind of an immediate success. This year, and by the way, we're going to, we haven't officially gotten AGU to have the Stephen Schneider lecture be permanent, but this year we will be, this coming year, we'll be putting in the paperwork to make that happen, and we're hoping to also make it a medal. And so we'll see how that happens. And the lecture that's going to be after this, in the next hour, is going to be a historical look at some of the science that Richard Somerville is going to give. We're also going to try to make a named lecture based on history and the history of global environmental change. And we're going to call that the Arrhenius Lecture. And I'll say more about that later. Anyway, it's a great honor to have another good friend, Ben Sander, be here today to give the Stephen Schneider Lecture. Ben is a physicist and an atmospheric scientist at Lawrence Livermore National Laboratory. We overlapped there when I was there for many years before I went to Illinois. He's in the PCMDI group there. His research focuses on climate model evaluation, the use of statistical methods in climate science, and he's particularly well known for the work he's done on detection and attribution of natural and human-related fingerprints in observed climate records. Ben has won a number of different awards, and I'm just touched on a few. One big one is this year he was named to the National Academy of Sciences. But he's also not only a fellow of AGU, he won the Lawrence Award from the Department of Energy, which is a big deal if you're at the DOE lab, a Distinguished Scientist Fellowship from DOE, the Norbert Gerbier, not sure how to pronounce that, award from WMO, and like many of us, shares in the 2007 Nobel Peace Prize for his work with the Intergovernmental Panel on Climate Change. Ben today is going to Ben's talk today is going to be a tribute to Stephen Schneider and an example of setting the scientific record straight, which is something Steve would love to have heard, I'm sure. Let us all welcome Ben Sander for his presentation. It's all yours.
Thank you, Don. Good afternoon, ladies and gentlemen. The real awards and rewards are the friends you make along the way. This first slide here shows that even from an early age, Steve was a master communicator. And in the next 35 minutes, I'm going to tell you a little bit about some very personal remarks about Steve, who was a good friend of mine. I'm also going to tell you about the last time I saw Steve, which was at a congressional hearing in front of the now defunct House Select Committee on Energy Independence and Global Warming in May 2010. And at the end, I'm going to play about 3 or 4 minutes from a recent video tribute to Steve, which was prepared by Climate One and the Commonwealth Club. First of all, some personal remarks. I love this song by Eddie Vedder from Pearl Jam. A mind full of questions and a teacher in my soul, and so it goes. And that was Steve. He had a mind full of questions. He was always trying to figure out, how are human activities affecting the climate of our planet? How will those human-caused changes in climate affect living things, ecosystems we care about? And how can we make wise decisions about the planet's future in the face of key uncertainties in the size and speed of projected changes over the 21st century and the regional and seasonal details of those changes? And he had a teacher in his soul. He reached thousands of people around the world. He had a profound influence not only through his scientific papers, and he published hundreds of papers in the peer-reviewed literature, but also through his public talks. Steve was prolific in reaching a variety of different audiences. He also reached people through his plain English books on the science of climate change. Many of you have read these books, I'm sure. Climate and the Co-Evolution of Life, Genesis Strategy, more recently, Science as a Contact Sport. He also reached people through his advice to 8 U.S. administrations. And you can see there some of the hearings that he participated in, congressional briefings, briefings to presidents. And of course, through his service to the Intergovernmental Panel on Climate Change. Steve was an integral part of all 4 assessment reports of the IPCC. And if he were around and here with us today, he would tell you about his his work on IPCC AR5 and his excitement about working on the next assessment report. After Steve's death, I had opportunity to reflect on some of the personal lessons that I learned from him. The first one is, never engage in science by assertion. Don't do science by eminence of position. It's not how high you are in the scientific hierarchy that matters. It's the quality of the science that you do. It's how good your ideas are. That's what really matters. And I'll show you an example of what I mean by science by eminence of position later. He also told me, choose the important problems, not the safe ones. I remember during the midst of my difficulties in the aftermath of the publication of the second IPCC report in 1995, 1996, when for a time I contemplated giving up science, Steve said, he took me aside and he said, Ben, you will know that you're getting somewhere in science by the number and quality of the enemies that you accumulate over time. And Steve, of course, had direct personal experience of that. Never be deterred by powerful opposition. Some things are worth fighting for. And a clear exposition of the science of climate change, that's worth fighting for. Steve was a master communicator. He's the best I've known. Never stop trying to communicate the basic science in plain English and find creative ways of doing that. Tell stories, use metaphors, communicate your passion for what you do. Talk to anyone about the science, even your critics, and always find time to speak to students. Steve was very approachable. If he'd be in the audience now, he would be whispering in someone's ear, "Ah, that's Santer, you know." He would talk to anyone, and he was always very, very generous with his time. He was also, in addition to his communication skills, a first-rate scientist. Jeff Keel, in summarizing Steve's scientific contributions, said Steve was at the vanguard of climate science. He made really important scientific contributions looking at the impacts of aerosols on climate, the impacts of clouds and the oceans on climate change, paleoclimate, the estimation of climate sensitivity, And we really intersected in looking at signal-to-noise issues, the statistical aspects of climate change experiments. So when you increase greenhouse gases in a computer model simulation, when do you know that the warming signal has emerged from the noise of natural climate variability? With his wife Terry and with a number of students, he later became very interested in the impacts of climate change on things we care about, the distributions of and abundances of plants and animal species. He also got very involved in the economic aspects of climate change, policy options for mitigating climate change, and trying to identify levels of dangerous anthropogenic interference with the climate system. Here are a few public tributes, some by people in the room. Paul Ehrlich, very good friend of his over many years, a giant in his field, a wonderful friend, a hero, and more. Mike Mastandrea, former student of Steve's. I realized I had met a brilliant scientist who possessed a unique talent for both explaining complex issues and encouraging others to care about them. And this was a red thread running through many of the public comments on Steve. This combination of climate science communication skills and first-rate science. Steve believed passionately in the evidence. He was always trying to bring people back to the science, to the basic facts. The example of the life he led will continue to be an inspiration. Richard Somerville, who will be giving the next talk, and a friend in the communication field, Bud Ward. Now we have one less giant among us and one less truly exceptional voice embodying both scientific excellence and extraordinary communication skills. These are from some private tributes that many of you will not have seen. From Ramanathan, his estimate for the net cooling effects of clouds was verified by cloud forcing estimates from the Earth Radiation Budget Experiment within 10%, 10 years after publication of his paper. From Jim Hansen, he is irreplaceable. Climatic Change, the journal Steve edited, was Steve Schneider and was an exceptional scientist. Steve was as tough as nails. And finally, from Susan Solomon, Steve said something that I'll never forget, that leaders in science have 3 I's: intelligence, innovation, and integrity. We've lost the truest leader we could have wished for, but remembering the 3 I's, as much as we lesser mortals can, will help us in our thoughts, keep him in our thoughts, and will enrich our lives. And finally, this tribute. As one of America's leading climatologists, Steve was gifted in his ability to convey to policymakers and the public the essence of complicated climate science and its implications for our future. His advice was valued by countless individuals, from students to presidents. Steve was also a wonderfully warm, witty, and generous human being, as well as courageous through devastating illness and relentless in his determination to do all he could for as long as he could. And that was from President Obama to Steve's wife, Terry Root. So my personal sense of Steve's legacy is he really made a difference in this world. People often tell you one human being, one individual can't make a difference in the world. I don't believe that. Steve made a difference in our world. His science, his actions, and his words forever changed the way we think about human influences on climate. That would be great. Yeah, we have our own little local signal-to-noise problem here. For me, Steve made us realize that we're not just innocent bystanders in the climate system, we're active agents of change in the climate system. And I think that our collective future is a little brighter because of Steve's science and because of his tireless efforts to tell people why our science matters. Once again, a mind full of questions. This is Steve and Terry in Australia birding, one of Steve's great passions, and a teacher in his soul. It's very gratifying to me that the IPCC has decided to dedicate the AR5 synthesis and assessment report to Steve Schneider. As many of you in the room know, Steve was all about interdisciplinary science, about breaking down narrow disciplinarian stovepipes, and it's extremely appropriate that the IPCC should take this step. If you want to learn more about Steve's science, Steve's life, how he impacted others, I would refer you to the Steve Schneider Symposium website. Many of you may know that this summer, in August, there was a symposium honoring and paying tribute to Steve. It involved roughly 200 people from all around the world, students, family, former colleagues, collaborators, and covered 15 different areas. Steve's contributions to basic science, to the IPCC, brief history of the journal Climate Change, and it wasn't just a retrospective, it also tried to look forward. How can we continue to make progress on some of the issues that Steve cared about? Again, this symposium website contains videos of all of the presentations and a lot of useful information about Steve the man and Steve the scientist. Okay, second part of my talk. As I mentioned, the last time I saw Steve was actually in May 2010 at congressional testimony in front of the House Select Committee on Energy Independence and Global Warming. There were 5 witnesses. The witnesses were Ralph Cicerone, Mario Molina, Steve, myself, and Professor Will Happer from Princeton. Professor Will Happer, in his written and in his oral testimony, made this statement, and I'm sure many of you have seen similar statements in local newspapers. You've heard politicians make these kind of statements. The theme is global warming has stopped. Over the past 10 years, there has been no statistically, I think he meant to say significant global warming. This is not at all what was predicted by the IPCC computer models. Professor Happer did not provide any supporting scientific documentation for this statement, and in my opinion, at least, this was science by eminence of position. And you can't do that, particularly not if you're testifying in front of Congress. So my colleagues and I, many of whom are in the room, Frank Wentz, Carl Mears, Mike Weiner, decided to do the science necessary to address this claim. Was Professor Happer's claim right? Well, it turns out that the basic issue raised by Professor Happer's claim is one of how long would you have to monitor changes in temperature in order to be able to discriminate some signal, some human response, some climate response to human influences from the noise of natural climate fluctuations, natural year-to-year variability associated with things like El Niños, La Niñas, and longer timescale natural oscillations of the climate system. How long would the record have to be? Well, as we've known for many, many years, at least 30 years, the identification of a human fingerprint on climate is inherently a signal-to-noise problem. And many, many people have studied this, looking not only at temperature, but at many different aspects of the climate system, using different models, different observational data sets, different statistical techniques. It's a signal-to-noise problem. And I'm going to illustrate this signal-to-noise problem using a simple example, using estimates of temperature changes in the lowermost 3 to 4 miles of Earth's atmosphere, the lower troposphere. We've made satellite measurements of atmospheric temperature change. Indeed, Frank Wentz and Carl Mears are some of the pioneers in this regard, using microwave sounding units. These are instruments that measure the microwave emissions of oxygen molecules. Those emissions are roughly proportional to the temperature of deep layers of the atmosphere. And by measuring at different frequencies, you can back out the temperature of different layers of the atmosphere. These are global scale changes, again, in the lowest few miles of the atmosphere, available since 1979. And you can see that there's an overall warming trend of roughly half a degree Celsius over the full satellite record. The blue line is from John Christie and Roy Spencer at the University of Alabama. For many years, their estimate based on these microwave sounding units suggested that there was global scale cooling of the atmosphere. As Carl and Frank and Matthias Schabel showed, those tropospheric cooling estimates were wrong. The Alabama group had missed two important effects, at least two important effects, the altitude decay of satellites and the effect of drift in the orbit of the satellites on the sampling of Earth's daily temperature cycle. So you can see that there's this overall warming trend for the full satellite record, but superimposed on that is a lot of noise. And most of the attention in this global warming has stopped narrative has focused really on the period after 1998. In 1998, you see that big spike. Why? That was one of the largest El Niños of the 20th century. On average, El Niños tend to warm the planet. Towards the end of the record, you can see that there are a number of La Niñas. On average, La Niñas tend to cool the planet. So, there are really two scientific questions we wanted to address raised by Professor Happer's claim. First of all, can computer models of the climate system, when driven by human-caused changes in greenhouse gases, simulate such 10-year hiatus periods with little or no warming? And the second is, if you look at the full 32-year satellite record and that warming of roughly half a degree Celsius, is that warming unusual relative to our best estimates of natural climate fluctuations on these long multi-decade timescales? Okay, so the first point is that there's a lot of noise. There are a lot of variability in the climate system, again associated with year-to-year changes in things like El Niños, La Niñas, and I'm going to illustrate this briefly by showing you 10-year trends that I've fitted to overlapping chunks of this 32-year satellite record. And the overlap of these trends is going to be by all but 1 year. So you're going to see these trends marching forward, and you'll also see that whether they are positive or negative or how positive they are depends on the start point and the end point of the trends. So here we go. And another thing to note is that there are very few negative trends. On average, because of the warming of roughly half a degree Celsius, most of the 10-year trends are positive. And you can see that the largest one actually ends near the time of that big 97, 98 El Niño, and now the trends are getting smaller because they're getting towards those cooler La Niña events at the end of the record. If you average all of those brown lines, those 23 individual 10-year trends, you beat down the noise of natural climate variability, and you get an average trend of roughly 0.15 degrees Celsius per decade. So, how did we try and address Professor Happer's claim? This is all observations. How did we look at the computer model simulations? The simulations we used were from the so-called Phase 3 of the Coupled Model Intercomparison Project. Currently, nearly 5,000 people around the world are using that archive of computer model simulation output. And we looked at so-called historical or 20th century runs. That's where these computer models are driven with our best estimates of human-caused changes in greenhouse gases, sulfate aerosols, carbonaceous aerosols, in some cases land use change, and in some cases natural external forcings, changes in the sun and changes in the amount of volcanic dust in the atmosphere. Now, most of these historical runs end in 1999 or in 2000. So in order to compare over the full length of the satellite record through to 2010, we had to splice the historical runs together with so-called scenario runs. We chose the so-called A1B runs to do this splicing. Doesn't make much difference if you choose other scenario runs. And again, the intent was to compare of the full length of the satellite record. If you don't do that splicing, then various pundits out there accuse you of hiding data and trying to deviously tinker with the comparison of model and simulation output. In order to look at the size of tropospheric temperature trends that we might expect just due to natural internal climate variability, things like El Niños and La Niñas, we looked at so-called pre-industrial control runs, sort of undisturbed Earth experiments with no human-caused changes in greenhouse gases or other external forcing mechanisms. So this just shows you briefly what these historical simulations look like. They're from 20 different models. The y-axis range is identical in each one of these 20 panels here, and you can see a bunch of different interesting things. Some of these models, like I said, have estimated volcanic changes in them, so you can see the cooling caused by the eruption of El Chichon in 1982 and Pinatubo in 1991. You can see that the levels of variability are quite different in these models, but they all show an overall warming trend. So what you can do is exactly the same exercise that we did with the observations. You can fit overlapping 10-year trends to segments of these model simulations, and you can build up a distribution of lower tropospheric temperature trends in these model simulations. And that's what this distribution looks like. And you can see that the distribution is skewed to the right because there is an underlying warming trend. But the key thing is that it has a negative tail, which I've highlighted here in gray. In other words, Professor Happer was wrong. He claimed that computer models, when driven by human-caused changes in greenhouse gases, cannot replicate periods with little or no warming. Clearly they can, just due to, again, internal variability. Depends on where you start the trends. Whether you start near a high point and end near a cool point. In the model world, like in the real world, we can easily get 10-year periods with little or no warming. And if you actually plot on this distribution the average 10-year trend from the observations, the thing that I showed you at the end of that little animation, you can see that for both groups, for both Carl and Frank, the Santa Rosa Remote Sensing Systems group, and for the University of Alabama group, the average 10-year trend is actually very close to the mean of the model sampling distribution of 10-year trends. So there is no fundamental statistical inconsistency between the model and the observations in terms of 10-year trends. Okay, next question. How large is that roughly ½ a degree Celsius warming trend of the lower troposphere relative to our best estimates of internal climate noise? Well, we can look at this in the same way. These are now these pre-industrial control runs or undisturbed Earth experiments with no human-caused changes in greenhouse gases or other external forcings. You can fit trends to these things too. They're of order 100 years to 1,000 years long, so you get a big distribution of trends, and you can do this on multiple time scales. This shows you such trend distributions fitted to these pre-industrial control runs on time scales of 10 years, 20 years, and 30 years. And here the thing to note is that the distribution isn't shifted to the right. It's centered on 0 because on average in these control runs there's equal likelihood through natural variability of getting a positive trend and a negative trend. You can also see another interesting aspect that the y-axis range is the same in these 3 panels. What that means is that as the trend fitting period increases, it's more difficult, just by chance alone, just by random fluctuations in the climate system, to obtain a large warming or cooling trend. So the size of the noise of natural variability decreases as you increase the trend fitting or averaging period. So if you put this all together and then look at the size of the observed changes in lower tropospheric temperature relative to the size of these model-based estimates of natural climate variability, this is what you get. It's a signal to noise ratio, and you can see that if you look on the 10-year timescales, the signal-to-noise ratio is very poor. It's close to 1. So it's easily understandable if you look at that first distribution up there in panel A, models and observations produce a lot of noise on the 10-year timescale. So we would not look at one individual 10-year trend in order to try and obtain reliable information about the presence or absence of a human effect on global climate. The interesting thing is that if you look over the full 32-year length of the satellite record from 1979 through to 2010, the signal-to-noise ratio, the signal-to-noise ratio is greater than 4. So that tells you that the warming trend of roughly half a degree Celsius is 4 times larger than our best computer model-based estimates of natural variability on this long 32-year timescale. I won't go into this, but we've actually looked at the issue of whether models on average, these CMIP3 models, systematically underestimate the size of natural variability on these multi-decadal timescales. We find no evidence that that is the case, either for lower tropospheric temperature or for longer ocean surface temperature records. Now, that work isn't definitive, but the message here is that the model-based estimates of noise on these long timescales would have to be seriously wrong in order to get a signal-to-noise ratio of 2 or less, and we find no evidence that that is the case. If anything, the model-based noise estimates are slightly larger than in observations. So just to summarize, I participated in a congressional briefing about 2 weeks ago, and one of the people at this briefing claimed that the scientific community, the climate science community, never addresses the claims and concerns of skeptics. That's without merit. Such a statement reflects an unfamiliarity with what our community actually does. We routinely look at claims that are skeptical, are critical of findings of a discernible human influence on global climate. We hold those claims up to the light. We don't dismiss them by eminence of position. We do the science necessary to address them. Carl and Frank and Mike Weiner and many of you in the audience have spent significant fractions of your career addressing claims that it's all the sun, for example. All observed warming is due to the sun, or there's no warming of the troposphere, or the last 50 years and the warming we've observed over the last 50 years is not unusual in a paleoclimatic context. We routinely look at alternative explanations for observed warming and try and see whether they have merit or not. I've also showed you that Professor Happer was wrong. His statement to Congress was incorrect. Computer models, even when run with human-caused changes in greenhouse gases, can simulate 10-year hiatus periods with little or no warming of the troposphere, or, as Mike Weiner and Dave Easterling showed, little or no warming of the surface. Finally, I showed you that the warming of the lower troposphere, that roughly half a degree Celsius over the last 32 years, is indeed very large, 4 times larger than our best current estimates of the size of natural climate fluctuations on those 32-year timescales. So the inference is that natural climate variability alone is unlikely to explain the observed change that we saw. I'll leave the final word to Steve here. This is from Steve's written testimony at that May 2010 hearing in front of the House Select Committee on Energy Independence and Global Warming. Science strives to reduce uncertainty through data collection, research, modeling, simulation, and so forth. The objective is to overcome the uncertainty completely, to make known the unknown. No doubt, further scientific research into the interacting processes that make up the climate system can and will eventually reduce uncertainty about the response to increasing concentrations of greenhouse gases. This is very unlikely to happen quickly. however, given the complexity of the global climate and the many years of high-quality data which will be needed. And then this was vintage Steve. Meanwhile, even the most optimistic business-as-usual emissions pathway is projected to result in dramatic, potentially dangerous climate impacts. That means making policy decisions before this uncertainty is resolved, rather than using it as an excuse for delaying action. And I'm sure many of you in the room have heard Steve say exactly that uncertainty is not an excuse for doing nothing. Moving to the third part of my talk, which will be a brief, roughly 3 to 4 minute excerpt from a video. What is this video about? 2 days ago, the inaugural Stephen Schneider Climate Science Communication Award was presented to Professor Richard Alley from Penn State. And this is bestowed by Climate One and underwritten by the Climate Works Foundation and Michael Haas. It's a $10,000 annual grant, and it's given to, quote, a natural or social scientist who make extraordinary scientific contributions and communicated that knowledge to a broad public in a clear and compelling fashion. Greg Dalton at Climate One was instrumental in the creation of this award, and if you want to find out more about it, please refer to this website. And at this award ceremony on Tuesday, Climate One had put together a roughly 15-minute video of some of Steve's appearances at Climate One and at the Commonwealth Club, of some of his public lectures, and we're now going to look at some portion of this, but I'd refer you to the whole video. It's really fascinating and very well done. Yeah. Sorry.
How did we know in the 1970s pretty much what would happen? It was theory then. And since then, nature's been cooperating with theory, but we kind of knew what was going to happen. You couldn't add 4 watts of energy over every square meter and have nothing happen.
Scientific consensus that CO2 will build up and will be a potential problem is very large, but a scientific consensus on precisely how influential it will be in 10 years or 20 years, what areas climates will get better, what areas will get worse, this is where the controversy comes in.
We also knew that you had to stop using the atmosphere as an unpriced sewer to dump your smokestack and tailpipe waste and your land use change interactions. All of that was known. It was not just in the club of 100 left-brain people. We testified to Congress, we talked to ministers, there were national and international meetings. It was out there.
Some of the things we're doing ourselves are accelerating the process. Our fossil fuel burning, coal, oil, gasoline, natural gas, is a very big contributor to the current greenhouse effect, pouring out not only vast quantities of carbon dioxide, but other gases like carbon monoxide and nitrous oxide.
So why didn't we succeed? What happened? Climate science is a system science. It's like trying to understand your body, or trying to figure out something with cancer, or how is the educational system going to work most effectively, and how are we going to do security. Every one of these complex systems problems has multiple components. And when you break them down, what you find out is rarely do we know everything, and rarely do we know nothing. So we have to break system science into the well-established components, which are settled. I'll tell you a few, into competing explanations where our work has been able to get us to winnow it down to 2 or 3 possibilities. Here's where the disconnect comes along. Special interests will grab what's convenient for their ideology or their position. So what you end up with is you end up with a cacophony, typically, of people selecting stuff out of context, and then you end up with the end of the world versus good for you.
Carbon dioxide is natural.
Carbon dioxide is what plants eat.
It is a part of the regular life cycle of Earth.
There's absolutely no point in trying to control the emission of greenhouse gases.
Life on planet Earth can't even exist without carbon dioxide.
Insect-borne diseases such as malaria will explode. Where it's dry, it's likely to become much drier.
We're likely to see hundreds of millions of what we'll call environmental refugees.
It has the potential to escalate into the largest global catastrophe mankind has ever known.
Climate change could take on a life of its own, and global warming would become a runaway train.
We'll have 8 degrees, we'll be 8 degrees hotter, and basically none of the crops will grow. Most of the people will have died, and the rest of us will be cannibals. Civilization will have broken down.
Systems of our civilization is threatened by
immediate threat to life as we know it.
I'll confess my prejudice. The end of the world and good for you are the 2 lowest probability outcomes. What we are looking at.
I think I'll stop there. I think it was appropriate to end this with Steve's voice. For those of you who knew him, I'm sure that he will live on in your memory, and the best way of honoring him is by fighting hard for the things that he really cared about. For those of you who did not know him, I hope that you will try and learn through his writings, through his videos, a little bit more about this extraordinary man. Thank you very much for your attention.
Well, it's really wonderful for us to have another great scientist like Ben to make this presentation. Now, we'd be happy to address any questions that you might have. Steve has a microphone up here, so if you could come up here to make your comment or question, it would help, then everyone can hear it. Want to just pick somebody?
Hey, Ben, thanks for the talk. Question that, sorry? Oh, David Lee, UCSB. There was a paper published within the last year that suggested that a buildup of aerosols within the atmosphere from Chinese emissions might be responsible for kind of the lower rate of warming in the last decade. Could you address that?
Yeah, so the question is, why is there this hiatus period? Why has there been relatively minimal warming since 1998? And a number of papers have been published recently that get at that various issue. The explanation you mentioned, a ramping up of Chinese emissions of sulfate aerosol particles, which tend to reflect sunlight and cause cooling at the Earth's surface, that's part of the explanation. Again, another part probably involves natural external forcings, changes in the sun's energy output. We know that over the last solar cycle, there's been this transition from solar max to solar min. Some of that cessation of warming or hiatus period is likely associated with that. Susan Solomon had a very interesting paper in Science a few months ago where she looked at stratospheric aerosols and was able to show that over the last decade, a number of small volcanic eruptions have, rather surprisingly, been able to loft dust up into the stratosphere. And instead of seeing some slow decrease in levels of stratospheric aerosols after Pinatubo, we've actually seen an increase over the last decade. That increase would cause negative forcing, would cause some cooling. So I think the thing is all of the above. It's likely not only one explanation for the relatively muted warming we've seen since 1998, but a variety of different factors. The real challenge is to try and quantify the individual contributions of an increase in Chinese sulfate aerosol pollution, increases in stratospheric volcanic aerosols, decreases in solar irradiance, natural climate variability. You know, as I showed, the fortuitous location of El Niños and La Niñas near the start and end point of the period that you consider. All of those things play some role, probably others too. And the challenge is to try and quantify the contributions of those individual factors. To my knowledge, nobody has really done that yet.
Say again. Oh, I'm Eric Weaver. I work at the National Science Foundation. In the case of the climate models, where you can see these things even in unforced simulations that go for 1,000 years, it's clearly natural variability. And I'm wondering if anyone has looked at those simulations to see what kind of natural variability. Is it really just all El Niños and La Niñas, or is there other things going on? And I think ideally what we'd really like is for the natural variability component of it to be predictable, so that, you know, at least when you testify to people on the House, on the Hill, you would be able to say, well, this is something that we actually can anticipate. Certainly presidents of countries like the United States, I'm sure would be quite grateful if you could give them a heads up that we're about to enter one of these hiatus periods, considering that it would probably last for their entire term in office.
Sure, thanks for that comment. Clearly, the variability that we see in these undisturbed Earth pre-industrial control runs is not purely El Nino variability. It's rich variability on many different timescales. A number of people have looked at the ability of these models to simulate variability associated with the Pacific Decadal Oscillation. Celine Bonfils, who's in the room here, has specifically looked at models' ability to capture important aspects of that longer timescale Pacific Decadal Oscillation variability. Other people probably in the room have looked at the ability of these models to capture variability associated with the Atlantic multi-decadal oscillation. And our best understanding is that models capture some important features of these modes of variability. Ken Sperber, who's also in the room, has looked at how well these models simulate the variability associated with the Madden-Julian oscillation. So the bottom line is we routinely look at how well these coupled atmosphere-ocean models capture important features of the amplitude, the structure, the time scale of key observed modes of natural variability. Now, the second part of your question addressed predictability. Can we say something with some confidence about how the exact trajectory of temperature or some other quantity over the next 10 to 20 years may evolve based on these modes of variability? And I think the answer is yes. We're currently gearing up for the fifth phase of this coupled model intercomparison project, CMIP-5, and that experiment will involve so-called decadal prediction experiments, where instead of using these coupled models to project changes into the future, you're actually making a forecast. You're initializing these models from some current state of the ocean. That current state contains information about the current state, if you will, of these modes of variability. So the hope is that those decadal prediction experiments will be able to give us some of the information that you requested. So to what extent is there some predictability associated with knowing the current state of the AMO or PDO?
John Nielsen Gammon, Texas A&M University. In the context of responding to claims made by doing real science to see whether they're correct or not, the sort of claim that was an example there was not one that would normally be made scientifically, but is made in the public policy arena. And so they're not necessarily the most important scientific questions, but they become very important scientific questions from a policy point of view. And it's something relatively new in our science. You've been very active in doing that sort of research. Do you think the community as a whole is doing enough to address these scientific questions that are address policy arguments rather than sticking with just advancing the science in isolation of the policy?
I'm not sure I fully understand your question. This hearing that I referred to was entitled Climate Science in the Political Arena, and Professor Happer was testifying as a climate scientist, even though he is not a climate scientist. So his testimony was about aspects of the physical climate system, many different aspects of the climate system. And again, I believe that if you are testifying in front of our Congress, you have a responsibility to get the science right. That is why my colleagues and I decided to address one scientific claim in Professor Happer's testimony. As I mentioned, many people in the room have addressed other flawed scientific claims, and I think we have a responsibility to do that as scientists, particularly when things are elevated to the level of congressional testimony.
My name is Dale Quattrochi. I'm with NASA at the Marshall Space Flight Center in Huntsville, Alabama. And I just happen to work in the same building as John Christie and Roy Spencer. And although we may view their science as being flawed, they do unfortunately have the ear of very important individuals in the Senate and the House of Representatives. If we go ahead and try to ignore what they say and hope they go away, that's one option we can do, which I don't think will happen. And if we go ahead and continue to criticize them, as well as the representatives, the senators that espouse their overall science, it raises their ire and kind of entrenches their personal beliefs of what climate science is all about. How can we overcome this? What kind of suggestions do you have?
Sure. Well, thank you very much for that question. And I think the best response that I have is this. I believe that John Christie and Roy Spencer did our community a service by providing the first microwave sounding unit-based estimates of atmospheric temperature change, the troposphere, lower stratosphere. But for many years, they claimed, based on their analysis, that the global troposphere was cooling. That claim was wrong for reasons that I've discussed. As I mentioned, some of the people here in this room spent many years of their career dealing with the difficult job of trying to replicate the Spencer-Christie findings, and they could not do that. And I believe that that's what's really important. That's what Steve Schneider wanted us to do. He wanted to bring us back to the science, not to just criticize and say, well, this can't be right, and trust me, I'm a bigwig professor here, but to do the science necessary to address the claim. And Frank Wentz and Carl Mears and others did the science necessary to address the cooling troposphere claim and show that it was wrong. I think that's what has happened with many things that John and Roy have published. John Christie was involved in a paper back in 2007 claiming that there was a fundamental statistically significant difference between modeled and observed tropospheric temperature changes. And Gavin Schmidt and I and many others in the room looked at that claim and found that the statistical test that these authors had applied to compare models and observations was wrong. It failed when applied to randomly generated data. Again, I think that's much more important than just criticizing people and saying, well, we don't believe this cooling troposphere claim. Do the research necessary to address the claim and see whether it has merit or not. And that's what I've tried to do, and I will continue to try and do. I do think, however, that being said, that many of these people do fulfill a useful role. It's like, kicking the tires in the car to see whether the car is trustworthy or not. And that kicking the tires of the car has forced all of us to do additional science to address the claims. But there comes a point when you got to stop kicking the tires in the car, when people have already showed you this car is trustworthy. And that's what I would hope from them, that they would have the ability to admit hey, when we first came out with these estimates of tropospheric temperature change and said that the uncertainties in these estimates were trivially small, we were wrong. The true uncertainties in constructing homogeneous climate quality data records from over a dozen drifting satellites, the true uncertainties are huge, and we admit that. That's what I would hope to hear from them.
Do we have any other questions? So there's one more here. How are we doing? Got a couple more.
My name is Brian Etling, and I'm actually a park ranger who's shifting into being a climate change communicator. And I'm one of the folks that saw Stephen Schneider as well as Richard Somerville on TV and got motivated to learn more about that. And I was just wondering, I never had that chance to have a beer with him because I always loved the way he could tell a story and just relate science to non-scientists like myself. And I was wondering if you could share any kind of funny stories or anecdotes. He was so great with analogies, too.
With Steve, it was usually a glass of wine.
Yeah.
Thank you very much for that question, and I will share two stories with you. The first one is about a beer that I shared with Steve. And the occasion was the November 1995 plenary meeting of the second assessment report of the Intergovernmental Panel on Climate Change. And after a long, exhaustive 3-day process, roughly 100 countries had finally approved this bottom line statement: the balance of evidence suggests a discernible human influence on global climate. And Steve was there. He played, as he describes in Science as a contact sport, an important role in the genesis of that balance of evidence statement. I had been on stage for over 8 hours. I had not had anything to eat or to drink. And Steve and others went to a restaurant. It was Madrid, so they're still open 1 a.m., 2 a.m. Let's go have a beer. And we had a beer, and I was just relieved that the whole process was finished. It was over. I could go back to being a scientist again. Little did I know. And Steve looked at me and said, "The world is never going to be the same. This single sentence will change your life." And he was right. He could see it. I could not. But he saw what was going to happen and what ripples in the ponds of science and politics and the media that single sentence was going to create. The second story is from the first time I met Steve. I was working at the Max Planck Institute for Meteorology in Hamburg in the late 80s. And I had been invited to a so-called Berlin Dahlem conference. Those are week-long conferences, and what happens is that you actually write the draft of a book during that week. This particular conference was on paleoclimate, something I knew nothing about. I had gone as an observer. And on the first day, what typically happens is they choose rapporteurs whose job is to write the initial draft of the chapter. I thought I was just there as an observer, as someone who could learn a bunch of stuff about paleoclimate, but I made the mistake of actually making some interventions and saying stuff, so I got saddled with the job of rapporteur. Steve was also in this particular group, and he took pity on me. As I mentioned, one of his distinguishing characteristics is that he had a lot of time for young scientists. And he took me aside and said, "Ben, I'm going to help you with this." So I remember all the other participants in this conference got to go to cool places like the Berlin Opera. And one evening, Steve was at the Berlin Opera, and I was back in the offices of this conference trying to write the first draft of this chapter. And Steve, while this is his multitasking ability, while he was in the opera, he had a go-between. He would be writing comments on various drafts of this chapter in the opera while while listening to the Berlin Philharmonic. and would be passing them to a go-between who would bring them to me, and then I would revise things and pass them back to Steve. For any of you in the audience who've sat next to Steve at scientific conferences and had him whisper in your ear all the time, you will know exactly what I'm talking about. But that story sort of summarizes his extraordinary ability to do a lot of things at the same time, and also his genuine concern with young scientists, a concern which I, and I'm sure many others in the room, have greatly appreciated.
Okay, I think we're going to need to call it quits. Let's thank Ben one more time, please.